Okay, and we are recording. Okay, last time we were talking about Riemann sums, and here's the big idea of a Riemann sum. Remember, it's kind of a rip-off of the idea of a single variable Riemann sum. What's the purpose of a single variable Riemann sum? Commonly misunderstood, be a outdated and heavy-handed, undesirable way to compute an area under a curve. Absolutely missing the point. It's not motivated by a desire to compute area under a curve. It's an expression that allows us to take an interval on which we have some question that we want to answer. Think big. Lots of different questions that we might want to answer that happen on an interval. Maybe I'm computing area under a curve, I suppose, but more likely I want to compute the amount of mass distributed on this interval, or the population distributed across that interval, or any of a variety of other different things. Point is, if there is a question on that interval, I would like to be able to use a strategy where I break it up into smaller intervals on which the answer to the question might look something like this. Now, of course, this assumes that the question actually does have this feature, that on a subinterval, that I can write it as being some function times the size, delta x, of that subinterval. Not all questions have this property. But if I can answer the question on a subinterval, and if it takes this form, and if the question also has a second property, namely that the whole is the sum of the parts, and that the answer to this entire question I'm interested in is the sum of the answers to the question on the individual pieces. Again, not to be taken for granted, but a huge number of questions have this property. It's what I call accumulation. The quantity in question accumulating over the interval. If it has that property, then I can add up over all the pieces to get this, and this particular algebraic expression then just happens to be exactly what I need to be able to write down to answer a huge category of applications. Okay, so short version of what I just said. This expression right here allows me to take a whole is the sum of the parts, chop it up, add it up, right? I like to say it in these various different ways. Approach to solving lots of problems. And this one expression answers a huge category of questions. Okay, so we want to do the same thing now over here for a rectangle. Is it because I'm interested in computing the volume under a graph? No, that's incidental. It's, I suppose, geometric convenience to visualize. It's familiar and nice, I suppose, but it's really not the point. What we're interested in is an expression that allows me to answer a huge category of questions that, again, have certain key properties, but a broad category of questions that just, as long as they fit certain properties, same basic properties. I need to know on each little piece that I can answer the question by this expression, namely some function appropriate to the application times area. Not width anymore. Width is appropriate to a one-dimensional, right? But size, in this case, the size of that piece is area. What are these questions that I might be able to answer as something times area? Oh, well, let's see, if I were computing volume, I suppose, then height times area would give me volume. If I were interested in computing the population of Colorado, well, then population density times area would give me population. If I were computing the amount of mass distributed across here, mass per unit area times area gives me mass. Right? So a huge category of questions that I can answer very conveniently on each little piece. And then second requirement, the same. I need to know that if I add up over the whole, right, then I get the answer for the whole. In other words, again, this quantity has to have the feature that the whole is the sum of the parts. And again, it's a very, very common feature to have. Population, the whole is the sum of the parts. Mass, if you chop up mass into little pieces, the whole is the sum of the parts. That's intrinsic to how mass works in the real world. So there are these little catches, there are these little details that we have to worry about, but basically this expression, as a rip-off of that expression, is a way that allows me to represent an answer to a huge category of questions. And again, don't pigeonhole yourself into just one thing and just volume under a graph. No, it's very, very narrow. Rarely what we're interested in. And I say we, I mean like engineers, physicists, and people doing applied kinds of things. Rarely are they actually interested only in volume under a graph. It comes up here and there, I suppose. But primarily we want to be able to answer a broad category of questions. Yeah?
Is it okay if you slide up to the previous page? I have a question that's kind of relating to that.
This up here?
Up further, sorry.
Okay.
It's in the last part of 5.1.
Oh. Okay.
Yeah, so in the second one, when you're trying to say mass, how is the dx dy? Wouldn't that technically be a change in area?
Yeah, but that's not what this is. No, I hear what you're saying, but that's not what this is. So this expression here is something that's a well-defined thing, right? This is an integral, right? And when I write this like this, I have to know what this integral is before I can start doing stuff with what that expression is. And the moment that you say, okay, well, I want to write down what this Riemann sum is and start playing fancy games with moving factors in and out, some surprisingly subtle and nasty questions come up. And so, now there is a way there is a way to make that work. But it's not what this says, right? So this very literally says a single variable integral. And I'm saying if you can't make sense out of a single variable integral, then it's not that this can't be computed or that this can't be connected to the answer to the question. It's that you can't write it down in the first place because the argument just doesn't make any sense. That's a great question, but you see what I'm saying?
Yeah.
Yeah, it's a nasty little detail. Yeah. Okay, great. Okay, so this is our big idea. We have a new expression that's going to play a role of our old Riemann sum. This is what I'm going to call a two-index Riemann sum because there's an I and a J describing where you are in the which slot are you in on the x-axis and which slot are you in on the y-axis. Okay, and it's going to come up a lot. This two-index Riemann sum. So we're going to develop a shorthand and a name for it. The shorthand, let's see. Say first. The name this is called a double integral. And I'll be able to motivate that terminology better in a few minutes. And the notation is this, and I think it's a pretty easy pitch in the same way that we use an integral symbol to represent a limit of a sum. Likewise, here I'm using two integral symbols. It's just notation to represent a limit of a two-index sum. You might think of it as you're adding up over two different indices. And then likewise, and I think this is also an easy pitch in practice, width times height is area. Okay. All right. Now, good news. The book gets more fussy with the definition than we're going to need in this course. In particular, the book worries about these issues right here of what happens if you use irregular partitions and what happens if you use what I'm going to call arbitrary test points. And it turns out none of this makes any difference for what we're going to be interested in this class. Now, if this were Math 431 or Math 531, we would absolutely worry about this stuff. And it absolutely makes a difference. But it only makes a difference if the functions aren't continuous. As long as they're continuous, it really doesn't matter for computational purposes. Anyway, there's a whole discussion that we just don't need to worry about. Okay, so y'all can ignore all of this stuff in the book. Okay, so let's see an example of this in action. I'm going to compute let's see, we've actually already answered this question, but let's do it again in a different way. I want to compute the volume under a graph, right? Sitting over a rectangle. Like so. Right, how would I compute that total volume? Well, first case I'm going to make, volume is an accumulating quantity. Volume accumulates over that area, by which I mean the total volume that we're interested in. Let me just kind of highlight all of this. This total volume that we want is the sum of the volumes of these, I like to call them French fries. That's where my head goes. Being associated to these little pieces of the domain down there, right? So if I chop up the domain and look not at the volume over the whole rectangle, but the volume over just a subrectangle, the total volume is the sum of all of these little volumes. Now, again, don't take this stuff for granted. Whatever the question is that you're looking at, you got to think it through and make sure that this actually makes sense. Here, let me give you an example of a question where this wouldn't work. Suppose the question were to compute the surface area of this volume, right? Is the surface area around the outside of this volume, is that equal to the sums of the surface areas of all of the individual French fries? Heck no, right? Not even close. So that question of surface area, that perfectly reasonable question, but it's not an accumulating quantity as you divide up the rectangle. But volume is. Is everybody on board? All right. Second little bit of good news. That answer to that question on that little piece is pretty easy to answer. I mean, pretty much, right? How much volume do we have in that French fry? Well, it's pretty much height times the area of the base. I mean, we can quibble over at the top it's not perfectly flat, and I suppose that does make a little teeny tiny little bit of difference. But in the limit, that's going to go away, right? A lot like when we saw similar analyses to the area under a curve question with single variable calculus. Right, so as far as the limit's concerned, this is basically a little tall, skinny, rectangular box, and volume is height times the area of the base. Is everybody happy? Okay. All right, well, it's all over with the shouting, because this expression right here is a 2-index Riemann sum. That is exactly what we have here. And that is therefore this double integral. Now, how to compute that is a separate matter, but just making the observation that to this question, volume under a graph, we have an answer of a sort. Is everybody okay? And various other questions that we can give answers to, and I will in a few minutes. But while we are here talking about volume, I want to point out something really useful, and that is I want to come down here and look at this diagram. And I think it's really helpful to draw the various objects of interest that we're playing with in this discussion and how they have connected in what ways. So let me sort of start with a reminder. We started off with, I'm getting ahead of myself. We started off just thinking about how to compute volume, just volume, right? And we figured out that there was this thing called an iterated integral, and in particular, if you want a volume under a graph, then boom, we know how to do that. We can turn volume under a graph into an iterated integral. Then I sort of enlarged the scope and said, hey, what if I want to talk about any of a bunch of other different applications? And we looked at mass in particular. And I made the observation, and this is what you were just asking me about, you cannot directly relate mass to an iterated integral. It doesn't make any sense. This just doesn't fit. I mean, when you look at the inside integral, we've got mass per unit area times length, and that's just not a thing that we can make a case about. We don't understand what that is. It just doesn't work, right? So don't make the mistake of thinking that you can just do that arrow right there. You can't. And that was where we found ourselves sort of in trouble. Okay, and likewise, of course, mass is not just the same as volume. They're two completely different things. If you want to make a connection between an application and the volume under some graph, you need something better. Okay. All right, so this is what we had so far. What we just did is think about this right here. We defined this thing called a double integral, and my very first example was to show that I can compute volume with a double integral, which seems silly because we already knew how to do volume with an iterated integral that I know how to compute. How silly is it that I would relate volume to a different construction that I don't know yet how to compute? Right? What's the point? Seems like we're going the wrong direction. Okay. As we were writing down double integrals, I also made the observation that all these other applications, many other applications, I will be able to connect to double integrals because anything that's an accumulating quantity, the whole is the sum of the parts, and where on any given little individual piece, it's a easy little question, some function times area, you can represent the answer to the question as that 2-index Riemann sum. Okay, so this is where we are. This is the objects and connections that we've drawn and the connections where we've tried and failed. Everybody happy so far? And you might be able to see where I'm going with this. This volume computation here, the point is not that it allows me to compute volume. The point is that if I can compute volume with two different expressions, those answers have to be the same. The neat upshot to which, the very valuable upshot to which is actually not about volume. It's that double integrals can be computed with iterated integrals. And now we actually have a way forward. We have a way to answer all of these various applications that we're going to be interested in. All of these different applications, how am I going to make sense out of them? Am I going to try to argue that they're volume? No, that doesn't make any sense. Am I going to try to argue that they're iterated integrals? No, that doesn't make any sense either. I'm going to argue that they are double integrals. I'm going to point out then that I can compute that with an iterated integral, and I can crank out iterated integrals with the fundamental theorem. So this is why this little green arrow matters. This little green arrow, at least in the way I'm presenting it here, this is what allows me to draw this yellow arrow. This is what allows me to connect the thing that fits with applications to the thing that I can get to answers. Okay. All right. How are we doing? Is everybody on board? Okay, so in some sense, at this point, volume has served its purpose. We don't really need volume anymore. In terms of solving problems, most of the time, you don't even need to look at any of this down here. This does not participate in our actual strategy of solution. Double integrals, though, are key. You got to have the double integral, because that's what connects to applications in the first place. And again, I want to emphasize this. This is mostly in service of applications. It's not mostly in service of pure math, formalities and stuff. Okay, all right. Okay, so when we're solving problems like this, I want to point out this really is a three-step process, and I need to see all three of the steps. I'm going to need to see in your solutions that you relate the application in question to a double integral, specifically a double integral. I'm going to show you a bunch of examples. Then I'm going to need to see, and of course you're going to have to do this anyway just to get the job done, but I'm going to need to see that you turn your double integral into an iterated integral, and then I'm going to need to see, of course, and again this is sort of obvious, but you're going to have to actually crank this out with the fundamental theorem. So 3 steps, they're all important conceptually in the context of this class, and please do make sure to do this. make sure you don't do the following. A lot of students will try to just do this and then that. And again, that doesn't make any sense, right? You can't just directly write down, oh, you want to compute a mass? Oh, okay, well, that mass is an iterated integral. Why? Doesn't follow. Keep in mind, this is not a class about answers. Whether you get to the right answer is not where points come from on exams, right? Where points come from is, do you represent a valid argument that actually holds water, right? And to make it a valid argument, you can't do that. Everybody see my motivation on that? Okay. All right. Let's see an example in action. Here we go. Let's see what my colors: green, orange, and blue. Okay. All right. So here is a rectangular sheet, and I have mass distributed across that rectangular sheet with the density given by some function there. Density depends on position in some way. And here we go. Phase 1 of the answer. Mass, the whole is the sum of the parts. On any given little piece of mass, mass is density times area. Nice and simple, right? I mean, if you know mass per unit area, given, mass per unit area means that that's what you multiply by area to get mass on a little small thing. And then, of course, you'll notice that this is right here, straight up the definition of a double integral. Okay. Step 2, let me skip this notational business down here. We'll come back to that in just a moment. Step 2 is to just kind of doff the cap to this fact that double integrals can be computed by their corresponding iterated integrals. And you can just cite that this is true. In fact, I have that here as a theorem. Right? This is the theorem that I kind of skipped over real quick. This theorem is just a recognition of what we have in our diagram, that double integrals are computed by iterated integrals. Slice in either order you like. Doesn't matter. Is that cool? Yeah.
So a double integral won't have bounds. It'll just have like a
correct
letter showing that area.
That's right. A double integral is simply defined on a rectangle, and that rectangle shows up just as a subscript. That's right. And a lot of people mistakenly think that, again, looking at this theorem right here, that these two things are defined as being the same. And they're very, very importantly not. Now, let me make the devil's advocate argument here. So the argument goes, well, isn't this the same as that? And doesn't that look basically the same as that? Right? And what this is an observation of is a motivation for these notations. Right? But fundamentally, these are very, very different things. This is a 2-index Riemann sum. What I have over here is a single variable integral, namely a 1-index Riemann sum, of a single variable integral, namely a 1-index Riemann sum. So as they are defined, these expressions are very, very different. Now, again, yes, they look the same. Yes, they always give you the same answer. That creates a lot of confusion about what they really are. Is that satisfying? Okay. Is everybody happy? All right. But yeah, they give you the same value, and so phase 2. Boom. It's, again, really just a doff of the cap to write that down. And phase 3 is plug and chug, and y'all already know how to do plug and chug. Do the integrals from inside out. Don't forget which variables are variables and which variables are constants. Yeah.
I had a question. So you have to write out the whole thing, right?
I'm sorry, one more time?
For like exams or anything, you write down both the left side and the right side. You can't skip a step.
You can't skip a step. You have to give me all three of these, all three of the legs of the argument. Yeah, absolutely. But let me be a little bit more specific about that. But I'm going to be a little bit more specific about that after I talk about this notation. So one second here. Okay, so let's talk about how we wrote that down. I mean, at the end, ultimately, what does this mean? It's just a shorthand notation to represent that, pretty much. Ultimately, what does this mean? Well, ultimately, it's just kind of a shorthand notation to represent that. So the argument can be made, as long as we're just talking about shorthands, why don't I go ahead and capitalize on the shorthand early on? It's nice. It's very handy. Very convenient. Everybody does it. You just have to make sure that you're clear when you write stuff down. So, for example, if I were to write down, as I like to do, I think this is a very convenient, very useful shorthand. When I write this down, don't make any mistake about what this represents. This double integral symbol here is just a shorthand convenience as a reference to this two-index summation. That's what this is. This doesn't say anything about antiderivatives. Right? This is a two-index summation. As long as you are comfortable with that, and as long as everybody reading knows that that's the case, then look how much easier it is, everybody wins, to just kind of write it like this instead of that. Not that you can't do the red one, but it's nicer, the purple one. Yeah.
So, going back to my question, you would start from like step 2 and 3.
Yeah. So here's what I want to see on an exam. On an exam, I want to see first that you recognize that mass is a double integral of density. Second, I want to see that you recognize that a double integral can be computed with an iterated integral. And then third, that you will compute that integral with the fundamental theorem of calculus. And that's where you just start cranking it out. Yeah, no worries. Is everybody okay? And again, don't forget to doff the cap to the double integral. I know it seems silly. I know, because when it comes to cranking it out and getting that answer down at the bottom of the page, you feel like, but this is what I really need to compute. You know, the iterated integral. Why can't I just write that down? Why do I have to write down this thing here that I'm never going to use? And the answer is because you unavoidably are using it, right? The double integral is the thing that makes this connect to your application in a meaningful way, and not that what you've written down is a bunch of garbage. Does that make sense to everybody? Okay. All right. So now here is another example. In this next example, really the kind of the point of the example is to note how convenient it is to use Riemann sum, sort of double integral shorthand notation for Riemann sums. So I made this example up, but I think it's a nice one. So suppose you are building some sort of a wall. I got the idea for this question when they were building our house, and there's a kind of a stone wall in the front as kind of the front facade of the house. But the thickness of the wall is not constant. And in some places, the stones stick out more and are bigger, thicker stones, and in other places, they're thinner. And I was looking at the guys building the wall and thinking, wow, that's a lot of stones to pick up off the ground and lift all the way up to where they are going to go in the wall, right? So they're doing a lot of work picking up the stones. How much work are they doing? Reasonable question to want to ask, right? So here's the big idea, and now real quick, note the setup here. I've got the XY plane set up like this arbitrarily, just to help me. Y is up and X is sort of across, and that allows me to kind of quantitatively describe where points are. And let's see here. Whole is the sum of the parts. Right? The grand total amount of work is the sum of however much work it takes to lift each stone. So I can divide up the whole task, which it's hard to get our hands on, and just view it as the sum of a bunch of relatively easy questions. How much work did it take to lift that one little stone right there? Okay, and thankfully works that way. Okay. Second, all right, how much work does it take for that one stone? Well, there's some differential amount of weight. How much does this little stone weigh? Right? It doesn't. We're not talking about the weight of the whole wall, right? We're talking about just this one little stone. And how far do I lift it is some distance. I can see exactly what that distance is. If this location is x comma y, the height that I have to lift that stone off the ground is y. Okay, cool. So, how much does that stone weigh anyway? And well, I've got a given here. That stone weight is proportional to the area. This right here is mass per unit area, or excuse me, weight per unit area, force per unit area. So that goes right there. And lo and behold, check it out, I have myself now a double integral. Right? The question that I was interested in, the answer is now I've been using this shorthand notation, but now I have literally a double integral. And namely, the answer to my question is where I add up a bunch of little short answers that are this expression times area. Everybody on board? Yeah, it's all over with the shouting at this point. Because phase 2 is to recognize that a double integral is computed with an iterated integral. Phase 3 is to crank out that iterated interval. Everybody happy? Okay. So again, please don't make the mistake of, again, you could still come up with the right answer, but lose a bunch of points by thinking that somehow it'd be reasonable to just kind of write this down and then go from there. And this skips really important ideas, right? That it does not directly make sense that work is involved. It can be computed with a single variable integral of something that you don't understand, right? The thing that you'd be taking a single variable integral of is not a thing with which anyone here has any familiarity with which they can make such arguments. Okay, so again, don't do that. Okay. All right. So, moving along. What if our domain is not a rectangle? Right, notice every question that we've asked so far, the domain has been a rectangle. How much volume is there sitting over a rectangle? How much work does it take to construct this rectangle, etc.? Okay. What if it's not a rectangle? I could still, very reasonable, want to look at a graph. I want to talk about how much volume there is underneath that graph sitting over some region. Even if that region is not a rectangle. That's a perfectly reasonable question. Is that cool? Everybody all right with that? Okay, well, what would we do here? How would I go about computing this volume? And I'm going to point out, we'll do the exact same thing we did before. This is just a slightly different shaped loaf of bread. And the volume of the loaf of bread is the sum of the volumes of the slices of bread. However weird the loaf might be shaped. Each individual slice, I can look at individually and argue that that individual volume of that individual slice is a cross-sectional area times a width, just like we did before. Nothing different at all. That cross-sectional area, I can again argue. Let's see here. Let me do this. The cross-sectional area is still an area under a curve, which means it's still a single variable integral. I mean, everything's the same. So no surprise that we're going to end up with an answer that looks, really, really like what we got before. In fact, there's only one little teeny tiny itty bitty little difference in the whole process. The fact that this is not a rectangle just leads to the following little weirdness. And I'm going to zoom in so I can see this better. Here we go. So looking at this here, let's look at the bounds, like this lower bound here. The lower bound for my dx integral. Keep in mind my dx integral is what's allowing me to compute that cross-sectional area. Right? X goes from some starting point to some ending point. And this starting value for x depends on where that is. Namely, where does my domain start? In particular, where does my domain start for that specific value of y? Right? And so here's the only difference. The only difference is that starting value now depends on y. It's now just not a constant. So I appeal to your geometric intuition here, and looking at my weird shape where I've got this, this starting edge, you might call it, is a curve. For this value of y, I get a certain value of x to be my starting value for my x integral. But if y were a little different, let's look at a value of y over here where y is smaller. Then notice my starting value of x, let's see here, for this starting value of y, for example, my starting value of x would be over there. It'd be a different starting point. That's it. It's the only difference. Go ahead and likewise the ending points. Yeah.
If you were doing a double integral with that, do you still just put r for the bound?
Yes, correct. But then there are some nasty questions. Okay, yeah, exactly. What does that mean? How do I define? When I define double integral for a rectangle, I made conspicuous use of it being a rectangle because I took the shadows and chopped them up, and the delta x and the delta y were always the same, and that's just very convenient. It does get a little hairy if you want to define a double integral for a non-rectangular domain. It's just not what Math219 is about. So what I'm going to do here is I'm going to basically wave my hands and say, trust me, it's fine, it's nothing to worry about, and just hope that you'll trust me. Because the alternative is that we'd have to go through a fair amount of ugliness. Yeah, and I think everybody wins if we just don't. Yeah.
And then also, if after you do the x part, if what's it called? Like the y part of the function, those are curved as well. Do you just replace d and c with
C and D have to be the extreme values of y, for which there's any cross section at all. And so that it doesn't really depend on anything. It's just looking over the entire domain. What is the very lowest value of y anywhere on the domain, and it's just some value. There's nothing for it to depend on because nothing's been chosen yet, because y is the first variable in which we're doing slicings. Yeah.
But if we chose to slice it the other way?
Yeah, totally. Then all the roles are reversed. That's right. Yeah, absolutely. Okay. So this is all you got to do is just ask in what way do these inner bounds depend on, and you're going to notice, just as a sort of a tactical point, I guess, these inner bounds depend on the outer variable. And we just have to figure out what are these functions. Now, how we go about figuring out those functions, we've got a process, but the first thing I want to observe is what do we need in the picture to actually answer this question. And the good news is we don't have to draw this ugly three-dimensional picture. As follows. What's my integrand? Well, my integrand is the height here. What's the height going to be? the height's going to be, well, whatever the integrand is from the resulting double integral. Now keep in mind, when we answer one of these questions, when we're trying to write down an iterated integral, we've already done some sort of a connection between the application and the double integral. So if you know what double integral it is that you're interested in, and you want to know what's the integrand for the iterated integral, well, that's the same as for your double integral. You can see it right here in this theorem. The integrand for your iterated integral is the integrand for your double integral. So presumably then, we already know the integrand. Now, if you already know your integrand, looking here, again, you already have the integrand wrapped up. The only other thing that we really need to know are these bounds. And these bounds, you're going to notice, the bounds, here they are, A, B, C, and D. The bounds only depend on the domain itself. Nothing that's vertical in this picture plays any role in these bounds. So you don't need to draw a three-dimensional picture. And that's where this next thing comes from. Notice I have the exact same domain here drawn where I draw just the two-dimensional part. That's it. Oh gosh. There we go. Right, just draw the domain two-dimensionally. Again, the integrand comes from the double integral. That's free information. So don't bother with the three-dimensional picture. Just draw the two-dimensional picture. And the bounds come from this. Now let's talk specifically now about how to find these bounds. There is kind of a two-step, 3-4-step process depending on how you count. Let's talk about the lower bound. Notice that the lower bound is just the x-coordinate of that point. What characterizes that point? Well, I can see from the picture that that point is a point on that curve. That curve is going to have some sort of an equation. Notice in particular, the bound that I'm looking for is an x-coordinate. So I'm going to solve for x, because that's what my bound is. Solve for x in that equation, and that'll tell you that bound. Likewise for the upper bound, and I'm just going to dive into an example. I think everything, you'll kind of get the feel of the process in the example here. So here we go. We want to compute an iterated integral, we want to compute a double integral here. In particular, I want to turn a double integral, double integral into an iterated integral. How do we do it? Before we dive into that, let me go back to our diagram real quick. Reminder, this is what we have. We're talking here just about this one part of the question. How do I turn a double integral into an iterated integral? I'm going to assume for these purposes that this double integral came from something, some context, that there's some application that we've already turned into this. Or maybe the question did that for us and just says, we just want you to compute this double integral. So this phase one part of the problem isn't really what we're talking about in this example. And then likewise, how to plug and chug, y'all know how to do that. So I'm going to focus just on this part right here. Okay, so let's do it. Let's talk about our domain. Here's our domain. On that domain, let's ask what is the range of values of x. By the way, notice I've made a choice as to which order to put my differentials. Basically an arbitrary choice here. I pulled it out of thin air. Doesn't matter. In fact, I'm going to do it the other way as my very next example. So don't worry about it. But anyway, I've made this choice. X is on the outside. These are what my x slices look like. Let me chop up my domain here. This is what my x slices look like. And the first one is there. The last one is there. So my bounds for the x integral I just need to know what's the value of x on this slice. What's the value of x for that point? 0. That's the origin, so x is 0. What's the value of x on this last slice? Now that's a bunch of points, but being as it is the last slice, all of these points have the same x coordinate. Now in this case, sometimes the fish jump in the boat, and the x coordinate of that point and the x coordinate of this point, you see, are the same x coordinate. They are both 1. Right? And so it doesn't really matter which point you look at on that last slice. Take your pick. They're all the same anyway. So our x bounds 0 to 1. Is everybody with me? Yeah.
Why is it D instead of R?
Why the what now?
Why is there a D instead of the R on the double integral?
Oh, D was the name of my my triangle is called D. So the domain is it's just called D.
Okay.
I named it R. You don't always have to use the letter R. Whatever the name is of your domain set, that's what the subscript is. That's how you indicate the domain.
I thought R represented like Riemann zones.
No.
Okay.
No, I'm sorry. That I can see where you would have gotten that. Yeah. No, the R. This R here it's R for rectangle.
Yeah.
R. So whatever this set here is called your domain. That's the set that you're chopping up the little pieces. Whatever it's called, I just use R for rectangle. Whatever it's called is what goes there.
Thank you.
Yeah, that's funny. That's a good question, and I've never thought of that before. All right. Let's see. Where are we? Yeah, here we go. Okay, 0 to 1. Okay, now as per our process, we're now going to fix a value of x. We're now going to look for our y bounds. So I want to know what's the range of values of y. Here's y. That's my x slice, and these are all the different values that y is going to take. Y is going to go from sort of there to there. So let's talk about the lower bound and let's talk about the upper bound. Let's start with the upper bound. Here's the upper bound. That's what I want to find the formula for. Well, it's the y coordinate of that point. That's where my sort of my slicing in the y direction is going to end for that value of x. Keep in mind, I'm only looking on this one particular x slice. Right? So for that arbitrary value of x, that's the point whose y coordinate is what I need. That point is on this curve. How did I know it was that curve? Well, because of the picture. You got to have a good picture. Right? The picture is what's going to tell you which edge of the triangle or which curve involved in the story is the one that you need to study for this particular example. That curve has that equation. Right, now let me remind you, let's connect the dots. And what I really want to know is this upper bound for y. It comes from that point. That point's on this curve. That curve has this equation. Now, where did I get that equation from? It wasn't given in the statement of the question. And well, here's where every question's different, and you've got to put in whatever legwork is necessary to find the equation of this curve. Now, in this case, I was given that point, and I was given that point. Those are given in the statement of the question, and then I do the appropriate algebra, right? High school algebra, and the punchline is the equation of that curve. Okay, now reminder. Where were we? Where is this coming from? What am I looking for here? I am looking for a value of y. I'm looking for a y bound. So within this equation, I need to solve for y. Lucky break, it was already solved for. Cool, life is good sometimes. You get lucky. You won't always get this lucky. Right? In general, this could be any weird arbitrary equation, who knows? But this example, done. So we've solved for y, and keep in mind what I'm actually looking for. This bound that I'm looking for is that y coordinate. And the formula for that y coordinate as a function of x is just x. Everybody good? Now this was a painfully slow, careful breakdown of, a lot of you might have been able to look at this and yeah, I can just kind of see it. You will not, in general, be able to just see it, right? It's important to see this as a multi-step process, because in those very many cases where you really can't just look at it, you need the careful process to get you there. Okay. All right. Likewise for the lower bound. Let's see here. Let's talk about the lower bound now. Let's see here. Our lower bound comes from that point. That point's on this curve. That curve has that equation. Again, why am I here? What am I doing? I'm trying to find a y coordinate. So we solve for y, and whatever I got there as I solve for y is my lower bound. Everybody happy? Yeah.
How would that be different if you selected like y1 being that bound and then y2 being like the highest x value?
Oh, you're talking about slicing it in the other order or something. So once we've decided that we're going to slice in this particular, let me clean up my mess and not get ahead of myself. Once I've decided this, then these bounds here have to be the largest and smallest values of that variable, and then the inner bounds have to be the largest and smallest values of that variable, with the understanding that you're focusing your attention on a single value of the outer variable.
Okay.
Yeah, because if you think about it, that's what this is, right? When we actually slice up the bread, right? Y the outer variable goes all the way across in some sense. The inner bounds correspond just to individual slices. Yeah. Okay. Okay, so we've got an answer here. Now, again, this is just for that particular choice of slicing of this one particular domain. Now, what I want to do now in the remaining minute and a half, and this should be fine, it's going to be super quick. What if we sliced the other way? What if instead of dy dx, what if I did instead dx dy? And I'm going to go quicker through this one because it's morally equivalent, but just sort of opposite. Y slices all kind of look like this, right? Our first y slice is here, which I think is pretty easy to persuade you is y equals 0. And our last y slice is here, which again happens to be exactly the y coordinate of that point, so conveniently 1. Now, we fix our attention now on a single value of y. We're going to focus on that value of y. Now, what's the range of values of x as x goes across there? Well, let's see here. The lowest value of x comes from that point. That point's on this curve. That curve has this equation. I am interested still in x, so I have to solve for x as a function of y. And the formula for x as a function of y is this. And this is where a lot of students will get it wrong. A lot of students will blow it because they're not thinking carefully about what the process is or what this thing's role is. This is not, as is commonly mistakenly told in high school multivariate calculus classes, this is not just the formula for whatever the lower line is, right? This is specifically how x is a function of y on that lower line. So it's y, not x. Wouldn't make any sense for that to be x. X cannot vary from x to something else. X cannot be both a ranging variable and also a fixed starting point. Does that make sense to everybody? Okay, we're out of time. Y'all have a good rest of your day. We will pick up from here next time. And make sure to come talk to me, or make sure I get you marked down for attendance.